This is the 13th video about wind turbines. In the previous video, we discussed the calculation of the annual energy production, or AEP, of a wind turbine. What we emphasized was that the AEP depends upon two factors. One is the power curve of the wind turbine, which can be computed using the BEM theory, or it is supplied by the wind turbine manufacturer. The other factor is the wind characteristic of the site, and we talked about how to characterize the wind using either direct wind speed measurements collected from anemometers or statistical methods based on the Weibull distribution. Once the AEP is calculated, we can compute another highly important number, the capacity factor. The capacity factor, which is just the ratio between the AEP and the total energy produced by the turbine under the condition that it is running at its rate of power, at its rated power for the full year. So that if the turbine is running at its full capacity, at its rated power for the entire duration of a year, and then what's going to be the energy generated, right? And then the capacity factor is just the actual annual energy production divided by if the wind turbine is actually running at its full capacity for 1 year. And by definition, this capacity factor must be smaller than or equal to 1. In the last video, we talked about the power duration curve. The power duration curve, which is the last slide of the last video, actually. So we looked at this kind of coordinates. Vertical axis is power, and then horizontal axis is the duration. Right? And we were actually so the area underneath the power duration curve is basically the AEP, right? If the wind turbine runs at its rated power for the full year, and then the energy produced is going to be the area that's underneath this red dashed line. Right? So if the horizontal axis is like 1 year, right, 8,700 hours or something, that kind of thing, right? And if the turbine is running at its rated power for the entire duration of the year, right, then the denominator of this factor is going to be the area underneath the red dashed line. Right. So the capacity factor is just the ratio between the area underneath the power duration curve of the wind turbine and the area underneath this red dashed line. The capacity factor is one of the most important numbers to consider when purchasing or selecting wind turbines for a specific site or specific wind characteristic. First, we don't want to buy a wind turbine that is too big for a given site. So bigger turbines has the capacity to generate more energy. But if it is too big for a given site, it's just a waste of money. So if at a site there, so we are looking at a low wind site, right? We are looking at a pretty low wind site. In the extreme case, if at a site there is no wind at all, then no matter how big the wind turbine is, the AEP is always 0 and the capacity factor is 0. So in this kind of extreme case, we don't want to buy a wind turbine for this particular site at all. In a more realistic situation, suppose at a certain site the wind actually blows for about 4 months. So the vertical axis is like 4 months. We're looking at a histogram, a wind speed histogram here, right? But this histogram just has a 1 bar in it. So the vertical axis is duration 4 months, right? 4 months. 4 months per year. It's blowing for like 4 months per year with a speed that ranges from like 5 meters per second to 10 meters per second, right? So we are comparing the one small wind turbine with 1 megawatt capacity and a large wind turbine with 6 megawatt rated power, right? So this large wind turbine certainly has a much higher rated power than the small wind turbine, right? So the denominator in the capacity factor of the large wind turbine is actually much larger than that for the small wind turbine. So in this case, the capacity factor for the large wind turbine is much smaller than that for the small wind turbine. And a huge amount of the capacity of the large wind turbine is just wasted at this site. And in this kind of situation, we would actually prefer this small wind turbine. Right? So if you have confusions about this kind of graph, the annual energy production is just the power, the actual power of the actual running power of the wind turbine multiplying the duration of the wind at a certain wind speed, right? So this vertical bar, the wind histogram, basically just tell you the duration of it. So if you just multiply the height of the bar with the corresponding power, and then do a summation over all the wind speed, then you get the AEP, right? So in this case, the AEP for the small wind turbine is just the area underneath this portion of the green curve, right? And for this portion, it's actually the area that's underneath this green curve, right? Just if you just do a multiplication. Of course, there's some sort of difference, right? So the difference, there's small differences here, but by just eyeballing it, we know that the AEP is actually might be slightly bigger for this smaller wind turbine actually, and then the denominator for the capacity factor for this small wind turbine is actually much smaller than the denominator for this large wind turbine. So the capacity factor for the wind, for small wind turbine should be a lot bigger than the capacity factor for the large wind turbine. Right. That's one of the considerations. We don't want to spend money on unused capacity of the wind turbine, right? On the other hand, we don't want to waste too much wind energy either at a given site. Right? So if a site has lots of wind power and lots of wind energy, we want to sort of harvest it as much as possible. So for example, if at a site the wind blows with a speed from like 10 meters per second to 20 meters per second for the full year, for the entire year, so the duration is like 1 year or something. Right? And then the small wind turbine still runs at its rated power all the time. Right? It runs at its rated power all the time. So its capacity factor has reached its maximum. That's the unity. Right? But for the large wind turbine, it's not really running at its full capacity rated power for all the time, right? But once it actually reaches its rated power, it can generate 6 megawatts. Right? For the small wind turbine, even if it reaches its rated power, right, it can only generate 1 megawatt. So even at its full capacity, the small wind turbine can only produce 1 megawatt. But the large wind turbine can produce 6 megawatt at its rated power once it is reached. So even though its capacity factor for this large wind turbine is lower than that for the small wind turbine, this large wind turbine can harvest more energy out of the wind. So in this case, the small wind turbine cannot capture the full energy potential in the wind at this particular site, and we would actually prefer the large wind turbine. So in practice, for a given site with a certain wind characteristic, a normal capacity factor should be around about 30%. It is important to remember that the capacity factor is not a measure of the wind turbine's quality. It depends very much upon the wind characteristic or the site. For the same wind turbine, if the wind turbine is identical, right, its capacity factor can vary substantially depending upon where it is located. And in this particular graph, the capacity factor can reach about 0.45 at the offshore site, where the wind speed is higher than that at the onshore site, for example, at this particular location. The capacity factor is just 0.18. Right. And that's capacity factors. Another type of curve the BEM theory allows us to compute is the so-called Cp-lambda curve. where Cp is the power coefficient and the lambda is the tip speed ratio. And here's an example of the Cp-lambda curve for a specific type of wind turbine, which is NKT 500/41, right? And it's computed using the BEM theory. Right? So the BEM theory allows you to compute not just the power curve, but also this kind of a so-called Cp-lambda curve. Right? Lambda is just the tip speed ratio, which is capital omega. That's the rotational, the angular speed of the rotor times the radius of the blade, the radius of the rotor, divided by u1. U1 is the free stream wind speed. Right? So the horizontal axis is lambda, and the vertical axis is the power coefficient. In fact, the Cp-lambda curve is quite similar to the power curve, except with two exceptions. One is that the horizontal axis is not the free stream wind speed anymore, but the ratio between the linear speed at the tip of the blade and the free stream wind speed. And the other difference is the vertical axis. Right? In the power curve, computed by the BEM theory, it's the vertical axis is the power. Right? But here it's not the power, but it's the power coefficient. It's the ratio between the turbine generated power and the power in the free stream wind power. So for this particular example, we can see that the peak power efficiency is about 0.5 or 50%, and it is reached at a tip speed ratio between 9 and 10, 9.7 or something. Right? And then so below this optimal tip speed ratio, the power coefficient, the efficiency decreases, right? And above this optimal tip speed ratio, the efficiency also decreases. Right? So the efficiency actually reaches a maximum at its optimal. You have a drop here. You have a drop at a tip speed ratio that's too large. Later on, we're gonna sort of take a look at this particular property. Right? It's actually different from the Cp-lambda curves that we have derived from the rotor disk model back in video 6, basically. Right? In video 6, the Cp-lambda curve doesn't have this drop in the efficiency at very large lambda, but now the Cp-lambda curve computed using BEM actually has a drop at very large tip speed ratios. So what's actually the utility of the Cp-lambda curve, right? You can use the Cp-lambda curve to choose the proper rotational speed of the turbine rotor. So if the wind speed varies, we can adjust the rotor speed, omega, capital omega, accordingly, so that the tip speed ratio stays within the optimal range. For this particular example, it's just between 9 and 10, right? Around 9.7 or something, right? We can always, when the wind speed changes, for example, if the wind speed increases, we can make a capital omega rotates slightly faster, so that lambda it remains at its optimal value, 9.7 or something. If wind speed drops, right, we can also decrease capital omega, the rotational speed, so that again the tip speed ratio lambda stays at the optimal range from 9 to 10, for example. Right? So this Cp-lambda curve allows us to actually control the turbine and make sure that it actually stays at the optimal state. Here's a different way of presenting the same Cp-lambda curve. It's the same Cp-lambda curve as in this particular figure. The only difference is that the horizontal axis has changed. The horizontal axis is not the tip speed ratio anymore. It's inverse. It's inverse. The advantage of using this kind of presentation is that the horizontal axis is now proportional to the free stream wind speed now. Right? So lambda actually equals to omega r divided by u1. So 1 over lambda is actually U1 divided by capital omega times capital R, right? So if you plot it as 1 over lambda, then the horizontal axis is actually proportional to the free stream wind speed. It might be easier for us to relate it to the power curve. We actually have seen this Cp-lambda curve before, right? Back in the 6th video, when we were discussing the rotor disk model for the wind turbine. This is a slide that I copied over from video 6. The power coefficient as a function of the tip speed ratio. In that particular video, we were actually evaluating the power coefficient as a function of the tip speed ratio, right? And it was obtained by evaluating this particular integral. We actually spent a lot of effort trying to actually evaluate this particular integral. Right? Here lambda r, this lambda r is the so-called local tip speed ratio at radius small r. Right? It's at a radius of small r. That's the local tip speed ratio. Right? It's a linear speed at the radius of small r divided by the free stream wind speed. Right? So at the radius capital R, that's at the tip of the blade, then lambda small r becomes lambda. Right? That's the tip speed ratio. This Cp-lambda curve does not have the drop. It doesn't have the drop. So it approaches the Betz limit infinitely. Right? So as we increase lambda, it gets closer and closer to the Betz limit. But it doesn't actually drop down. It doesn't drop down at very high lambda. So it's kind of different from the BEM theory that we have from the Cp-lambda curve computed using the BEM theory. The rotor disk model that we discussed in video 6 only accounts for the conservation of linear momentum, which is basically inherited from the actuator disk model that we discussed in the 5th video, actually. And also the conservation of angular momentum by taking into account the rotation of the wake. So the rotor disk model just accounts for these two conservations, the linear and the angular momentum. Right. But the BEM theory is actually much closer to the reality than the rotor disk model. In the 10th video, we talked about two very important corrections. The Prandtl's tip loss factor due to a finite number of blades, and the Glauert's correction for high values of A. So in realistic BEM calculations, those two corrections are actually included. Right? But here in this particular analysis that I'm showing here on this particular slide, it's an analytical comparison. So we are not including, we do not include these two very important corrections. But again, in realistic BEM calculations, those two corrections should be included. In the 9th video, we derived the torque acting on each of the rotor ring. Right. This is an expression for the torque acting on every annulus ring. Right. And here the CL and the CD are just the lift and drag coefficients for the particular airfoil that's used at the cross section located at the radius of R. Right. So small r is the radius of that particular cross section, that particular airfoil. Right. And then phi is the angle of the relative wind. It's the angle of the relative wind with respect to the rotor plane, the rotor disk plane. UREL is the relative wind speed. Small c is the core length of the airfoil located at that particular cross section. Capital B is the number of blades. Rho is the density of the air, and R is the radius of the annulus ring. Right. So the power generated by the ring is just the torque multiplying the angular speed, capital omega, of the rotor. Right. And then the rotor generated by the entire rotor disk, the power generated by the entire rotor disk is just an integral of the power contributions from all annulus rings. So the power coefficient, Cp, is just the ratio between the between the rotor generated power and the free stream wind speed. Here U1 is the free stream wind speed. Right? It's just the ratio between the rotor generated power and the free stream wind power, basically. That's the free stream wind power. And if we actually bring the representation of dq into this particular expression and carry out the integral over r, right? And not exactly carry out the integral, but convert the integral over r to an integral over the local tip speed ratio, lambda r. Here lambda h, so here RH is actually the radius of the hub. Right? So in the ideal case, the hub has a 0 radius, right? It's just the 3 blades. Right? But here we are actually accounting for the hub actually has a finite radius. So the blade, every blade has a base, right? And the base is sort of attached to the hub. After some algebraic manipulations, we can actually sort of obtain an expression for Cp, the power coefficient, right? And it looks like that. It just looks like that. This is the expression. So if we actually compare this particular expression that we just obtained by applying the BEM theory without considering the 2 important corrections, then this expression that we have obtained for Cp actually looks very similar to the Cp that we obtained in video 6 using just the rotor disk model, right? Using just the rotor disk model. Right. So in fact, if we actually look at this particular expression in the red box, right, this expression, that's the only difference basically. That's the only, if the expression in the red box is exactly unity, then this expression becomes identical to the rotor disk expression for the power coefficient, right? So when does the stuff in the red box becomes unity, right? It's a unity subtract something. So if this something becomes 0, then the stuff in the red box becomes 1. Right? So when does the thing that unity is subtracting becomes 0? Right? So if we consider CD actually equal to 0, so the drag coefficient becomes 0. Then this term becomes 0, and the entire thing in the red box becomes unity. Right? And it also depends upon cotangent phi, right? If CD is not 0, CD has a finite value. Right? The drag coefficient has a finite value. Then the entire thing in the red box depends upon cotangent phi. Phi is what? Phi is the angle of the relative wind with respect to the rotor plane. Right? So it equals to what? Back in video 9, again, we have in video 9 we have an expression for tangent phi. Cotangent phi is just the inverse of tangent phi, right? And we have an expression for cotangent phi too. Right? And this expression can be converted into the tip speed ratio lambda. Right? So as lambda actually increases, so cotangent phi also increases. Right? And cotangent phi increases, cotangent phi times multiplying this thing increases. So once subtract this thing, decreases. If it decreases, you multiply with this thing, and then do an integral over all the lambdas. Right? The entire integral actually decreases. So here you don't have the drop, right? But here, using the BEM theory, you have a drop. This drop is essentially caused by the aerodynamic nature of the wind turbine blades, and which is actually encapsulated in this particular term, right? Which includes both the drag and lift coefficients and also the cotangent of the angle of the relative wind.